Hello friends, today I will discuss about low impedance restricted earth fault protection relay for transformer. Before going through this video, you are requested to please go through my channel and do subscribe my channel if not subscribed earlier, and also press bell button for notification of videos to be uploaded in future. Before going through this video, first discussed about what are the criteria for high impedance REF relay. The criteria are that is all the CT ratio, that is phase or bushing CT ratio must be same with that of the NCT ratio. Also the knee point voltage of each CT shall be same. The second one is common, that is connection shall be proper as per polarity, that is P1 shall be connected to the bus side and P2 shall be connected towards transformer for phase CT or bushing CT, and for in CT or neutral CT P1 shall be connected towards the earth and P2 shall be connected towards the neutral point of the transformer. Number 3 is the resistance must be used in series with the relay for preventing relay operation under through fault condition, considering one of the CT is under saturate condition. Number 4 is the use of metro seal, that is to limit the peak voltage developed during fault condition. Metro seal must be used if the peak voltage is greater than of 3 kV. So these are the criteria required for high impedance REF relay. Now why should we go for low impedance REF protection? Consider a case that is the phase CT or bushing CT ratio is not same with the NCT ratio, and also the knee point voltage is not same with that of the NCT. Therefore we must be used for low impedance REF protection. In that case the relay cost is more, but the external wiring is very simple. Advantages for low impedance REF protection. Number 1 is there is no need for dedicated CTs. That is for example, if the phase CT or bushing CT ratio is 600 by 1, then if I use NCT of ratio 100 by 1 or 200 by 1, then all the calculation of the CT ratio correction will be done in the relay. So the CT cost is substantially reduced. That is the NCT ratio is lower that was required for the high impedance REF relay. So cost of the CT is reduced. Number 2 is the wiring is simple, as it does not require any external resistor and metro seal. Only the CT secondary inputs are taken into the relay. Number 3 is it provides internal CT ratio mismatch compensation. It can match the CT ratios up to 1:4, resulting flexibility in substation design and reduced cost. That is all the CT mismatch is calculated under the relay by providing a factor, that is K is equal to neutral CT ratio by phase CT ratio or bushing CT ratio, which will calculate all the CT mismatch, and it will take the primary value or convert the CT current in the same base value. The differential current is defined by the IDIF is equal to vector sum of all the three phase current plus K into IN. Here IA, IB, IC are the secondary value of the current, and IN is the secondary value of the NCT current, and bias current is defined as the I bias equal to half of maximum value of IA, IB, IC plus K into IN. This is nothing but the scalar value, that is under through fault condition or under fault condition, among the IA, IB, IC whichever is maximum, this maximum value is taken plus K into IN is taken for bias current, where K is the factor is given by the neutral CT current, neutral CT ratio by line CT or phase CT ratio. So all the CT input is taken in the same phase value. So the factor K is implemented, and IN is the current measured by the neutral CT, and the allowable range for the K is equal to 0.05 to 15 for standard CT. The characteristics of low impedance RF relay has been shown in this diagram. Here ID or differential current represent in the y-axis, and the bias current is represent in the x-axis. The flat area of the characteristics is the minimum differential current required to cause a drift signal for low bias current. Here IS1 is the minimum operating current, which is set as 10 to 20% of the rated current. From the first knee point onwards, actually there are two knee points. From the first knee point onwards, the operate current increases linearly with bias current, as shown by the lower slope, that is K1 in the characteristics. This lower slope provides sensitivity for internal fault condition. Normally K1 is set is 20%, 0 to 20% depending on the CT ratio error. If there is no ratio error present in the CT, then K1 can be set as 0%. If CT mismatch or CT ratio error present, then it can be set up to 20%. From the second knee point towards, that is from IS2 is the second knee point. Normally it is set as rated current of the winding of protection. The operate current further increases linearly with bias current, but at higher rate. The second slope provides stability under through fault condition. Normally K2 is set as 150%, that is 1.5. Now let us take example for low impedance RF protection of 10 MVA 33 by 11 kV transformer in LV side. HV is delta connected and LV, that is 11 kV side, is star connected. Here ID is given by vector sum of IA plus IB plus IC plus K into IN, where the phase CT ratio is 600 by 1 and NCT ratio is 400 by 1. So factor K is equal to NCT ratio by phase CT ratio, which is comes as 400 by 600, which is 2 by 3. So we can see that the ID is calculated in the relay in the same base value, that is in terms of phase CT ratio. So in the K into IN, the secondary value of the NCT is converted to the primary value, and then it is divided by the phase CT ratio. So all the CT ratio mismatch is eliminated by the factor K. So under normal condition, IA plus IB plus IC is equal to IN. Since so the ID, that is the differential current under normal condition, is comes as 0. So it's remain in stable condition. Now consider a fault occur in the blue phase under through fault condition. This fault current will flows towards the neutral point of the transformer. It enter the earth point and comes to the neutral point and flow towards the direction of the phase CT or Bushing CT from P2 to P1 and towards the fault point, as shown in this diagram. So maximum through fault current in the LV side is equal to given by rated current in the LV side by percentage impedance. Now percentage impedance is 10%. Considering 10% PI, the maximum through fault current comes as 5250 ampere. So the primary current that is flows in the blue phase, which is 5250 ampere from a direction P2 to P1, but in case of NCT, the same current flows, but the direction is from P1 to P2. Since ID is given by vector sum of all the three phase current plus K into IN, so this sum of this phase current and plus factor K into IN comes as 0, since the blue phase current flow in the from the direction P2 to P1, but in case of neutral city the direction is opposite of that of blue phase current, so ID is 0. Now under this condition, what is the value of the bias current? Bias current is given by the 0.5 into maximum of IF, IB, IC. Here blue phase current is maximum, that is here the blue phase means IC plus K into IN, and the blue phase current in terms of secondary value comes as 5250 divided by 600. Here value of K is 400 by 600 and IN is equal to 5250 by 400. So the bias current comes as 8.75 ampere. So friends, this is all about low impedance RF protection. So if you like my videos, then do subscribe, and thank you for watching my video.